what I want to do now is go to David Perez. Let me do a brief introduction for a man who needs no introduction. Okay, so for the last 7 years now, the Quantum Electrodynamics R&D team has been developing a proprietary variable electromagnetic drive that compresses the fabric of space. The VEM drive requires no liquid propellant that chemical and ion drives require to move through space. The team has performed replicable demos of the VEM drive that can produce up to 3 pounds of pull solely on battery power, and has plans to construct a more powerful set of drives capable of autonomous lift for space propulsion. So David Perez joins us to provide the latest details on their research and progress. And let me see, David is here. I will spotlight him for everyone. Sir, welcome back. Thank you very much. And thank you for being flexible on the schedule as well.
Yeah, I just happened to see the phone message and said, okay, it's an hour early. No problem.
Yeah, you know, one of the things that I found is some of our guests run way over and then others run way under. And so, you know, I just kind of try and do the best I can, but thank you for showing for us, sir.
Bet. I have a PowerPoint presentation if you'd allow me to share my screen.
Yeah, try the green screen share button right down there.
Right. Okay.
And okay, and it looks like you are already spotlighted, and so the PowerPoint should come up as soon as you do the share screen on that. And then I'll mute myself out.
Okay. I don't know how many people have seen any of our work that we've done.
Perfect. Looks great.
I've been this particular PowerPoint goes through the beginning of what we have done.
Oh, David, do you want to try and let me see? It's got a big subtitles thing on the right. It might be a little bit bigger if you close that. Or you could try doing screen. You could try doing screen share mode or slideshow mode.
How's that?
That looks great. That looks great.
This way we can have the flexibility of going back and forth in the slides instead of going in a sequential order. I mean, I already have them in a sequential order, but it depends on people's questions at the end, you know, how we can flip back and forth. If this is okay, we can go ahead.
No, that's perfect. That's perfect. Okay. Yeah, I think people can see it great. And thank you again, sir.
Yeah, no problem. Pleased to do it. One of the things that we've discovered is that nature really kind of aids in a lot of our understanding about, well, in this particular case, physics. It's been one of these situations where actual thunderstorms produce antimatter, which is a recent discovery. And 2007 was the first inclination, 2010 confirmation that antimatter is actually created within thunderstorms itself. The other thing that's interesting about where we've developed our engine and using nature as the basic syllabus, look at it that way, how to actually do this. Thunderstorms actually produce tripole fields. And this is a not that recent of a discovery, but 1984, Earl Williams from MIT, a atmospheric scientist, discovered that studying the electric fields and thunderstorms, that the top of the thunderstorm was plus, middle was minus, and the bottom was plus. And therefore, plus, minus, minus, if you want to look at it this way, of a dipole, an inverted dipole, plus, minus, minus, plus, and called that a tripole field. And so what we found out through empirical studies was that there were several pilots that claimed and documented effects that as they flew through a certain thunderstorm situation, many of these occurred, well, they occur all over the world if the conditions are right. If they have a lot of solar winds coming in, You have the separation between in the coal areas of high and low pressure systems, where you can generate what I refer to as mega thunderstorm inducements are created, and you get a bidirectional flow of electric energy from space and from ground to space. And particularly when you get closer to the equator, like 20 degrees north latitude or south latitude, but at 20 degrees north latitude, we have documented cases of thunderstorms erupting with the equatorial propagation of electrons that occur. And this was actually discovered during World War II for radio propagation. So there's historical note of empirical results of radio transmissions back and forth being able to be bounced off the atmosphere. But the indication of these high energy levels occur into the atmosphere itself. And in the December timeframe, particularly at the 20-degree north latitude area, one of our most documented cases of Bruce Kernan was actually went through into a thunderstorm at Bimini Island. He was surrounded by thunderstorms. He was coming back from Andros Island. And what had happened was in this circling around his aircraft, he couldn't go above it, couldn't go below it. But during the last buildup of these two thunderstorms, he found a hole at about the 10,000 foot level, and he saw blue sky on the other side. Now, as a pilot, you would never want to go through that, but as a last resort, he took it. And it was either that or eventually just crash into the ocean. So he went from Bimini Island to Miami Beach in basically a second. And this was one of the initial discoveries of you want to call it anecdotal, fine, I don't care, it doesn't make any difference, but the science of taking this into the laboratory and doing it, duplicating it, it worked. And so the crossing over of these tripole fields induced a non-sustainable local space warp bubble. And with that said, the aircraft got caught up into this and ended up flying 100 miles in about a second. And the wings held on the airplane, and that's 360,000 miles an hour. And to go from Andros Island to West Palm Beach in 47 minutes was pretty remarkable, since it takes 75 minutes in normal flight time. He actually went further distance in that flight time that he had taken. And bottom line was he ended up with 9 extra gallons of fuel on board his aircraft that wasn't expended, which would have been expended during that 100-mile hop. So the bottom line was something happened. From 75 to 47 minutes, that's 319 miles an hour that he would have had traveled. The wings would have fell off the airplane. He would have had structural cracks at 220 with these A36 Beach Bonanza that he was flying, was brand new in 1970. And there wasn't too much of an explanation other than beginning to do the investigation. This was heavy detective work, really, and trying to figure out into the atmospherics and potentially what really caused this to occur. And what we find out is that he was not the only person to ever have had one of these occurrences, but significantly enough, we have a C-97 supposed to take 6.5 hours on a flight, actually only took 5. And these aircraft only travel just a little over 200 miles an hour, some modified V-29, the C-97 aircraft, and they went from Kwajalein to Guam back in 1966. And so we have records of indications of similar occurrences. Arthur Godfrey, some of you may remember him as an entertainer, but he was a naval aviator. And he had an experience when he was going from Alaska to Japan. met a similar type situation as Bruce Kernan did flying through the clouds, and got into a sucker hole and ended up in Japan a half hour early of his normal flight time that he would have experienced. And of course, we also go back to World War II with the Tiger Moth case, where he was doing weather radar tracking experiments in the early part of the war in 42. And the bottom line here was he got caught up in an afternoon thunderstorm in London. And he ended up flying into a sucker hole and saw blue sky on the other side of it, took the aircraft through, and ended up in northern England. He flew back, landed, reported it. Nobody believed him, but he wrote up this thing and wrote up the letter, and his family had forwarded to actually Bruce and then to me of this experience that he had. I did look up, there was a radar experimental Tiger Moth group in England at that time during the war, and they flew these type of aircraft. So it was an open wing or bi-wing aircraft, open cockpit. And again, these related stories from World War II to basically present day. These are the actual numbers that Bruce encountered. His particular case is probably the most documented case because he had his all the flight maps. I have his refueling tickets. I have everything that shows a evidence, the path of evidence here, and people seeing him take off and see him take and land. His clocks on board his aircraft match the ground clocks. So this also relates into Miguel Alcubierre in 1994, where he had theorized about warp bubbles and how you can use warp bubbles to travel in space. And so what was interesting here is that things that Alcubierre talked about were some of the identical things that Bruce Kernan experienced. And the fact that didn't experience any type of momentum inside the aircraft when he entered into this bubble that formed around as a result of the crossover of the electric fields of the tripole fields of the clouds, and that he had a feeling of slight weightlessness as this thing began to occur around his aircraft when he was in the sucker hole. And as he came out, you guys were talking about ionization and how that affects things. Apparently his aircraft got covered in an ionized field. He calls it electric fog. And when he got to Miami Beach, the fog dissipated around the cockpit of the aircraft. And this has been experienced by several pilots, documented in the past as well. Is it related, unrelated? It's all related into the electric fields of these, the ionization that occurs inside these clouds, and the powerful amount of energy, like 10 to the 15 watts of power that you can get in one of these thunderstorms. It goes up to about 68,000 feet. I've measured these personally on radar up to 80,000 feet when I was in the Air Force. So these things are not unusual in that area of the world. Are they common every day? Well, you get thunderstorms down there, particularly, during the winter time, will cruise up easily to 60,000+ feet. But depending upon conditions, solar winds, also helps to energize these isolated development of these thunderstorms. And so I figured out the actual forecast parameters for these things, helped in moving this particular concept back into the lab. One of the ideas that we had initially was to take a UAV, Bluebird 2, which is the design that I have an actual prototype of in the garage, and was to fly this into the thunderstorm, have a chasing aircraft on front and back of the storms, and simulate this again, or try to recapture what Gernon went through back in the 1970s. Well, everything was set up. People decided to drop out. It was too dangerous. So I was left kind of holding the bag, so to speak. And so what we did then at that point was, well, look, if this actually occurs naturally, then we should be able to demonstrate and take this into the lab. If it's real, great. If it's not, okay. Then we thought a good game and tried to prove it. Nothing happened. However, that wasn't quite the case. So whether you have matter or energy, you can bend space. I mean, this is a statement of general relativity. So that's been proven beyond a doubt. And here we have is Miguel Alcubierre with his concept in '94 and his formulas of how this can happen: compression of space in front, expansion of space in behind. And so what we found was we had indications in the lab that this actually does occur. And I'm going to show you some of the signatures that we actually picked up here. These are all formulas that you probably have seen these onto the internet, inflation theories and the warp metric that Alcubierre had come up with. And he's more from a perspective of going from point A to B. But what we actually discovered in the Bruce Gernon's flight is that you don't go in a straight line, that mass actually influences, in this case, a warp bubble. And so he went in at 10,000 feet, he came out at 10,000 feet, which was a lot different than what theory would lead you to believe, is that you follow a straight line. And if he did follow a straight line, he would have ended up in outer space. If he hadn't have gone in the direction he was going and took that warp bubble, or the hole, the sucker hole, he would have ended up 100+ miles out into the Atlantic Ocean if he was going the opposite direction. And he would have more than likely been lost, ran out of fuel. Anyway, bottom line was taken into the lab. So this is what we do. We built an interferometer, we built some tripole antennas, and we use frequencies that I've done a number of programs for National Geographic and Discovery and History Channel, and taking that opportunity, flying in the aircraft into the Bermuda Triangle, which, you know, could be in a circle, it could have been a square, could have been anything. So, you know, they keyed off of the triangle name and a big mysterious thing. Anyway, bottom line is we replicated frequencies that we had flown into these clouds on careful measurements, 6 to 7 megahertz at the base of the cloud, VHF frequencies into the freezing level of the clouds, gigahertz frequencies at the top of the cloud. Well, an actual thunderstorm is a cadre of frequency, quite fascinating. But we concentrated more into the near freezing level areas of where this sucker holes began to overlap, or the fields crossing over each other. And so what we found out is when we passed the laser through these things is that when the system was turned on and we had a projection screen, we would get the fringe patterns from the interferometer. When the system was on, the laser would shrink, would be compressed into the screen. And when we turned the system off, the laser expanded. And this kind of gave us our first inkling into this. And we also then did a frequency analysis, and we found out that there was a redshift going into the exciter, or the antennas, that was measurable. And so we also took that part of the information as that compression, redshift. And then what we also did was we set up an experiment with the early form of one of our etched motors And we set it as far as 140 centimeters away from the box with the torsion bar. We call it the modified Cavendish experiment. In Cavendish, he actually had some masses on the outside of the sealed case, and he could actually measure universal gravitation, taking that concept that I had done an undergrad study in a permit that I was working there at Oswego State. I took that same kind of concept and I adapted it to this. And I said, well, indeed, if this thing is really doing what we think it is in compressing the fabric of space, then it should affect a free form or a freely available torsion bar that had equal weights. And we put ferrous material, non-ferrous material in on the torsion bar and ran the experiment. And we would start at 30 centimeters and then work our way out to 140 centimeters. And this took hours to do because we had to get the torsion bar to settle back down from movement. And we found out that the compression of the fabric of space can actually go through solid objects. So it wasn't an electrical a charge, because we had non-ferrous material, we had ferrous material, and the actual rates of movement were pretty much, curvature was different power levels at 25 watts, 100 watts of power. So we're getting movement at 25 watts with non-ferrous material at 140 centimeters. So we figured out swing rates, we videotaped all this. So that led us on to saying, well, if we can make these smaller motors and they have this kind of an effect at this level of power, then what can we do with other? So we developed a throttle, the full exciter, and then we went into the this next one here, where we actually went into our linear amplifiers, and we were able to develop up to 2,800 watts of power in our linears. So we would take the exciter and just like a car, an accelerator pedal, was to adapt this and run it under battery power. So we ran the whole system with 48 volts of battery power, about 160 amp hours worth of capacity, and able to power up 4 linear amplifiers, tune it to 50 ohms with the cabling that we had to the motor. The motor would use the exciter up to 3 watts of power, and for each of the linears, total of 12 watts of power. And we also had computer control in here where the software can actually turn the system on and off. Later developments, later designs are going to allow us to set thresholds in software. We'll turn the system on and off in case of an event occurs. Because when you experiment, you just want to save your equipment. You don't want to blow it up. And so that's what we've actually constructed. And on the design board is actually a quad throttle that we can actually manipulate 4 engines at a time on a lifter. And that's one of our new concepts and where we're headed. And that's part of the update that we're going to give you. But I thought it might be necessary for some of you who've never even seen any of this. Where did all this come from? It comes from nature. And we replicated what we saw reported in nature and was able to replicate it in a lab in a micro environment versus a macro environment. So this is the exciting part of it. You also were mentioning earlier in some of your discussions, you were talking about the cold area outside of the spacecraft and the gyro, I think they call it, or the Tic Tac. Well, those cold areas literally are experienced by us as well. I'm going to skip ahead, but because you guys talked about it, we get the same effect. It's almost like a Peltier effect, and that this is the air before, and we cool it to 5.5 degrees inside the V of where the fractal arrays are located. I found that kind of interesting, is that our thermal infrared camera did the same thing as like what the F-18 Hornets picked up on those spacecraft. So that could lead to some additional conversations from everybody here, theorizing or whatever, but we have seen the same effect. So we have redshift. We can go through solid objects, influencing other objects. And here's the start of the update of, I'll open it for some questions right now before I get into what we're actually headed towards, what we're doing.
Okay. Well, actually, David, typically we do the Q&A at the end of each session. Do you want to run through the whole thing and then we'll come back after that?
Okay.
Okay.
That's all right. Well, write them down. Write them down. Write those questions down.
Perfect. Okay.
All right. This started actually in 2010, but the actual, the thought process and investigation started actually before 2010. But the process of actually building hardware and conducting the first experiments was the first results that we ever got, October 15, 2012, at 6:05 p.m. I know because right after the experiment, my brother called me out of the blue, and I noted the time. I said, well, this is kind of historic or significant. And we actually got the laser to compress onto the screen, onto the fringe patterns, and we did a bunch of calculations for that, whatnot. But that was the first indication that something brought in from anecdotal pilot reports and testimony there was some real guts behind it. Then the World Herald came in and they did a videotaping, and they did pictures of the experiments, of the effects of the motor moving the independent masses on the torsion bar. They were the first to actually record that live, and the movement of the engine. So that was a banner day. They published that on New Year's Day, that paper article, or December 26th, I guess. Yeah, the actual date of it came out just around New Year's. Everybody was talking, made it to Reddit, actually. And since then, our whole goal was to improve the efficiency of these motors and increase the power, more power, Scotty. And that's exactly what we've done. So we have capacity now up to 2,800 watts of power. And we're going to be moving into 5,000 watts of power it'll just take a longer period of time, but we've submitted an unsolicited proposal to NASA to try to seek funding for further development of the VEM. And this means scaling it up. So we've gone from a 7-inch model to a 2-foot model. And the 2-foot model, model 17, actually produces 3.37 pounds of pull. And we've been able to lift it, and we've been able to pull other objects into a solid case again, replicating the experiment over and over again. And our conclusion has been, in looking at the power and the resultant movements, is that it's exponential in nature. So that can we take this and get to faster than light? My speculation is that at least the data shows us that we could do it. It just requires a significant amount of power, probably in the neighborhood of 100,000 watts, somewhere in that range. Right now, it looks pretty good on the lower end of where the exponential curve, 5,000 watts, you get us several hundreds of pounds of lift. That's what we're after with this. Anyway, as we moved along, we proved that we could scale it up. Still worked from smaller motors to bigger motors, and that the efficiencies is it frequency dependent? That's another study that we want to do. What are some of the unique actions of the effects of the VEM drive? Is that is basically as we have the warp signature of the craft, we're able to literally map out. We set up a sensors, 55 sensors. We use 10 watts of power above and below Model 15 engine. Got this data, and the graphic is basically the engine is underneath the fields of compression. So the tripole fields here are compressing the fabric of space, and behind it, that 4-inch level above and below, we measured a gentle relaxation. It's not an actual push, as Alcubierre indicated with his theory. However, our engine is operating a lot different than what I believe that he was proposing of a compression of fabric at space of an engine that not only compressed in front, but also in the back expanded quickly. So pushing, quote, the warp bubble. What we found is that not necessarily the key to create a warp field is that you can literally compress it in front and move the craft, or in this case, the engine. We have videotapes of that you can go to our website, QED-NE Nebraska, and you can see the videos for yourself, read the papers, and it's hours worth of reading and looking at stuff. But anyway, that significant signature we accomplished this past summer, and the one on top was accomplished 1.5 years before that. It took a long time to collect the data. There's thousands and thousands of points every quarter second on the run that we make. And so the bottom line was, as we made significant progress, this is the kind of goals that we wanted to achieve here with the 3.37 pounds of pull. We want to develop within the next year is a 10-pound variant with a 45 Newton pull capacity. And that we want to be able to test a variety of different fractals and frequency configurations to find out what is the true optimum frequency that we would need to construct a motor with and acquire a proper FCC frequency license for that. I'm a ham radio operator. I'm using experimental frequencies I'm authorized to use in a Faraday cage. So if anybody's out there, well, you're violating it. No, I'm not. I'm fully legal and I'm doing it. We also want to develop this a quad lifter. And one of the other more expensive aspects of this proposal is we want to deploy a 100-kilogram microsat to space for operational testing and to up orbit from the initial orbit in space, taking a ride with SpaceX, $2 million. Not a cheap aspect of this, but the idea is we can get the unit into space, then it would look similar to this. So solar panels, expand communications, motor up on top of it would be deployed in a package. So all these things going on within a 5-year time frame. The name of the satellite is dedicated to Esther Goddard, the wife of Robert Goddard, father of modern rocketry. And she was instrumental in taking all of his data sets and generating a 3-volume set. I don't know if anybody has actually read those books, but they're more than just fascinating of this single man development of an entire space program. So we named and dedicated the satellite, if it comes to pass, or we actually build it at some point, dedicated to her, instrumental in his evolution of discovery. One of the other practical sides of this, in addition to what we're trying to achieve, is station keeping for satellites and future space stations using VEM drives. There's no propellant, use only battery power or any electrical source, and that it's very economical. I mean, an ion drive is over $40 million to deploy that in space. Neon gas, which is rare. They are making some new ones with iodine and or krypton gas that Elon Musk has used in his little satellite deployment for internet. We're looking at this as more of a practical thing because there aren't any moving parts, and there's no propellant. The fact that there isn't any wear and tear on the motors after hundreds of hours of operation. So artificial gravity, you know, one of the big complaints going in space is that atrophy of exterior limbs, exercise, hours worth in the space stations and the ISS. Well, by putting these underneath the floorboards of the spacecraft, 10 to 20 watts of power, which will, and we've done biological tests, it has no effect on well, it wouldn't have any effect on the humans, but we've also used these very sensitive flies, laboratory flies, and they actually had no effects after being exposed to the motors at 1,000 watts of power. The future generations of these flies showed no malfunction, you know, what I'm trying to say is nothing different than what a normal generation of flies at eating habits, nothing to note. The same death rates on the control group to the actual exposed group. So that experiment, radiation experiments with Geiger counters, and that we got a 1.1 microrad increase from the motor at 1,000 watts of power, which is got to 8 to 12 microrads is the normal background radiation on the Earth. It go as high as 56, 80 with Fukushima, and when I had my radiation monitoring lab set up. Anyway, bottom line is it's biologically nil, nothing. The other ideas that we have is to not just produce artificial gravity for spacecraft, but you can literally have a bubble, a warp signature within a warp signature. So from the context of a warp bubble around a spacecraft, you can utilize these warp bubbles inside the spacecraft for artificial gravity. So we think that this is should be a pretty eye-opener for people on being able to utilize this more for just propellant or for movement of a spacecraft. Now, from a terrestrial environment, the next step is to go retrofit if the engines can be made bigger and additional power available to retrofit aircraft, possibility, designing new spacecraft and aircraft to facilitate the engine development. This isn't, you know, we're probably 10 years out, perhaps between 5 to 10. We're looking at doing our stuff within the next 5 years to get it to a point where it's more than just significant. And ultimately, I don't know about all of you, but I want to do FTL, and I believe it's possible. Anything else? engine design, power availability, all of that. But I believe it will either be within my lifetime, and I'm almost 70. My family lives a long time. I got maybe another 20, 30 years. I don't know. But within that time frame, I'm hoping to see this. And got to have dreams, or else you can't move forward. Yet. Anyway, the quad lifter is a terrestrial adaptation of the motors, so that we can 10-pound lifters on each one of these, and that we found an RG cable 400, super lightweight. I don't know if anybody's familiar with it. It's used in aerospace, in the military. It's extremely lightweight. It's like 0.06 pounds per foot. Double shielded, very expensive stuff. Anyway, we're gonna want to hook that up into our lifter, power up the VEM drives, lift that off the ground to see on a tether. Essentially, you're using the cable to go to 30 feet off the ground or more, and then to subsequently put our miniaturized linears that we're designing in the craft like this, so that we can fly it around. Now, can we do it? Well, we've been pretty successful so far. Miniaturization, as technology advances, we've been able to take advantage of the new power chips that have come out. Increases our relationship, but we also produce an awful lot of heat, and that means we're going to have to cool them down with like Palantir diodes, cooling chips. Now, with our standard engine, well, I call it a 3.37 pound motor. The calculations that we've made, doing the same run that NASA does, in the short run to Mars, takes them about 10.5 months with some of their spacecraft. We can do it in 18 days. We can get to Saturn and Pluto in 147 days. Project Horizon took 10 years. The 10-pound variant get us even faster, and it's a constant acceleration. And what we've actually noticed, we've pulsed this engine, and when we've actually done that, the power is going. We get about a 2-second peak in power, even after the power is turned off. It's something I haven't been able to research. I haven't dedicated the time in the research yet to look at what is that function. Is it puddling of electrons, kind of like in a magnetron tube in a huge radio transmitter, or is this an effect of the fabric of space bouncing back? We're seeing this push. But we've seen the motor advancing in its suspension hanger for minutes. But again, we're not making any claims. Something weird is going on there, and it's going to require some research. But we're opting for a large walk-in Faraday cage where we can set up multiple workstations, so that we can do multiple testing all at once and try to solve some of these issues. This is model 17. It's actually 3D printed, and the fractals are mounted onto the board. This is hand wired, this particular model. And Mark Sokol has offered and graciously helped us out with one of our new solid state designs, which I'll show you in a bit. But one of NASA's new next ion drives that they have just developed can produce 0.236 newtons of power, but it requires close to 6,000 watts of power. And the engine that we have requires 1,500 watts of power at 15 newtons of force. And what's interesting is one of our earlier models, model 15, which was 1.26 pounds of force we're able to measure with the motor, required 1,650 watts of power. And so the new variant is not just lightweight. This particular engine variant weighs just a little over a pound, which has allowed more movement in its suspension, in its hanger, measuring of movement, which we thought was interesting, because an ion drive in terrestrial environment doesn't move at all. You can't even move a Kleenex with an ion drive. So we're getting the movement, and we're using crude measurements here to move masses, 1.5 pounds and 3.5 pounds of mass through solid object. We're able to move several millimeters. And again, that kind of an influence, as demonstrated to us at least, is that what we're doing is real, and that the redshift friction of the fabric of space influence through solid objects to other objects on the other side becomes pretty interesting. So as we took these measurements, we also came up with magnetic field, curvature, and gravity data. And the sensor, the Adafruit sensor that we do, is a tri-axis accelerometer. And so we got these results. And then we did the bottom sheet a year and a half later, and then saw the expansion, or I call it the lazy expansion, of the fabric of space behind it. So again, gave us some very interesting results. I know there was a kind of a flap recently of a signature of a warp bubble, which was retracted, I guess. But we've had this for several years now, at least the first indicator of the compression of the fabric of space for us. And you're probably all wondering, how the hell do you do this? Well, it took a bit took years to figure it out, but cross fields from thunderstorms, and that's what we emulated on these arrays. So the perpendicular emanation of the propagation of the signal comes out from the fractals themselves. And if you're not familiar with fractals, fractals are a device which can literally take feet worth of an antenna array and reminiaturize it. And that's what we were able to do. One of the big problems was, all right, I can set up these antennas, I can simulate this with low power, I can get all these measurements. How do I turn this into something that would be practical? And working a long time ago with the Atmospheric Science Lab, Dr. Brown, believe it or not from Back to the Future, but was real interested in fractals, caught my interest, and we had lots of discussions, and we talked about antenna arrays and all this. One thing led to another, and I read a paper from a scientist from MIT, who has fractal array antenna company, developed a fractal array for his apartment for ham radio operations. He wasn't allowed in his apartment an antenna, so he came up with this unique idea, made a fractal. Well, now everybody's doing it, bending wire and making fractals, miniaturizing their antennas. But we took this a step further. So we took the VHF frequency, and I mapped that out and constructed the fractal I've seen in one of these engine. I'll relate back to it real quick. And you see these things. This is a modified Cott curve, as they would say. And this is tuned specifically for the frequency of use in the VHF spectrum. And these have worked quite well for us. Spacing is critical. Spacing between the V shapes into the arrays, we've done 50 degrees to 75 degrees. You can affect the fields by either strengthen fields, reduce the field strength by the movement of these flexible V shapes. So variable, that's where the variable VEM electromagnetic drive comes in, of how we were able to accomplish this. This has 4 tripole fields mounted on these arrays. We could go for more, but we kind of kept it to the simulation of what a thunderstorm actually is. So that's why this particular configuration. I'd like to experiment more and go beyond this as well. So the bottom line here is, as we said, energy and matter are equivalent. In this particular case, this overlap of the field causes a compression or a side load to go down into the bottom of the antenna arrays. And this is what causes the compression, near field crossover. Now in radar, you have near field, far field, reflective power, all this. No one's done work in this area of crossing near fields over. And I guess we may be the first, I don't know, maybe there's somebody out there, but we're the first to apply this into an operational device. And it's been very successful in replicating the occurrence of this and doing all kinds of different data measurements, and with results of the pulling force of these motors. The signature pattern that we ended up getting, thermal patterns of the cooling effect, like a Peltier effect around the engine of 5.5 degrees, significant. 3D effect or 3D printing effect to lighten the weight of the motors. The original motors were etch boards, didn't weigh too much, about 1.5 pounds. And the larger variants that we made were over 10 pounds. And we came up with this more lightweight solution because everybody kept saying, hey, you got to show us movement, man. You can't just measure in a hanger with spring scales on here and showing the downward movement of the motor. You got to show us some physical movement versus millimeters. Well, that's what we came up with the idea to lighten it up. And so we've gone from engine model 1 to now engine model 19 and variants in between there. And you can notice that we've reduced the fractal on the plus minus side. So we got plus minus plus, plus minus plus. So we're emulating more realistically what the actual tripole fields look like in thunderstorms. This hasn't been tested. I've had some medical issues and whatnot. That's delayed testing of this particular model for over a half a year. Actually, it's been longer than that. But I'm back on the thing, and I'm getting back into ready and roaring to get out and start to test again. So health issues become a problem in doing research. This is one of our articulated models that we're going to be producing using Model 17 design. We're going to cluster. We're going to put them in a quad. And these then can be manipulated and angled in any and all directions, going backwards, forwards, side to side, going in towards the center. We don't know what would happen if all of these engines were pointed in towards the center point. We don't know whether to take warp insurance or not on our lab. I don't know. It's a possibility. It's a little eerie because we're doing a lot of unknowns. And at this point, when we get to this level, we're going to be able to get over 5,000 watts of power into this unit. And it can go into a canister. I know, and everybody's saying, hey, it looks like the engine pods on the Enterprise. Well, literally, we got to be able to mount these things. The idea here is that the antenna arrays, if I were to take quad loop Yagis, for example, the gain you put by doubling the amount of loop Yagis is very tiny. It's only like 30%. But the engines themselves are standalone, whereas and again, we don't have any proof of this yet. And that's why we want to cluster them. We want to find out, can we maintain that 3.37 pounds in the Model 17 configuration? And each one of the units themselves, as they interact and create the compression fields, are we going to get an actual 12 pounds worth of force being able to be measured out of these motors? Or is it going to be a percentage of the cluster? It's unknown. I can't tell you that. I'm not even speculating on this. We hope it's the latter, and we get 12 pounds out of it. But that would also be beneficial, is that one could actually use these units in clusters and power up spacecraft. So if we had a 10-pound variant, you want to put 100 of these together? Yeah, it's faster than light possible at that point. I believe by being able to, using the clustering technique, we might be able to achieve some incredible speeds within the solar system itself. And that's one of my big goals, is to see the actual basic economy of space blossom. Because if you can't get places from point A to B in any timely manner, waiting 10 years to get to Pluto to get maybe some raw materials from there, or going to the asteroid belt 16 Psyche, for example, to get to there, we need to be able to process the material, like from off-Earth mining corporation. They have robots that can mine asteroids like that, but they can't get there yet. If we could get them there and get them back and forth within just a few days, we could get ore and precious materials that we need here to process onto the Earth to further our technologies, and let space blossom as a new economic base. We wouldn't have a lot of these problems we have on Earth. At least that's my little take on the matter. So space is the future, and what I have here is some comparisons between the motors. You can see these in the paper as well. But within 20 seconds, we can generate well over 15 newtons of force. And we have the various models that are listed there from the Dawn spacecraft, NASA EM drives, Hall thrusters. Some of these things take up a tremendous amount of power where we really don't require a whole lot to do what we do. And what we've done since the early investigations of last year, we've gone into a new configuration, an rack-mounted configuration. And this is a nickel steel cabinet. And so we're trying to reduce any and all problems encountered with cabling and all this. And we've gone to a lot of trouble to put it all and put in air conditioning as another factor to keep equipment cool, because obviously it runs better. It gets like 130 degrees in the garage, and it can get whatever the ambient air temperature is in the winter. We've had -20 here, so I don't run the equipment past 8 degrees Fahrenheit just to protect it. But if I had multiples of everything, I could care less. I'd run it at 20 below. Eventually, it has to go to space at 200 below. I'm just kind of biting my time here. We need more equipment. Money, that's what we need. These are the linear amplifiers before they've been wired up. And this is the combiner. This is where we can generate a lot of power. This configuration alone is 2,800 watts of power with our new amplifier chips that we had recently put in to update our equipment. And this is the software package that we've developed, and the throttle controls, and the software can actually control this and can turn the system on and off. The future evolution development is to set limits. So if we see any points of reflectivity coming back of power, we can set the limit. If we wanted 50 watts reflected power on the cables, the system would turn off automatically. There wouldn't be any particular damage to the linears. They can take up to like 400 watts of reflected power before they burn up. And we have done that, okay? And that's, these linears are, I almost don't want to even say what the price of making these things are. It's in the tens of thousands of dollars. That's a lot of teaching I have to do in order to pay for those. And you blow one up and it's like $4,000 just to replace a lot of the burnt up parts. It's you all know this. If you're building anything, you know what's going on out there. And then this is the concept of the quad throttle design. It looked very similar to this with slider bars and LED lights on the side. Real nice, right? In the graphic. But it just shows what our future is looking like. This is the newer lab. We ripped it out about a year ago, last summer, and we redid everything. So we increased the space, throw away stuff, and we need more space. We couldn't even hardly move between workbenches. Now we actually have 4 feet between the benches, and we can actually move around without bumping into each other. And my wheelchair can actually get in and out of them easier now, which is a temporary thing to do. This one here, and then this is how it would look inside a spacecraft underneath the floorboards. And one of the interesting things here, I don't know if anybody has ever looked or investigated gravity doses. That's the new lingo that they have out there. We can produce at 20 watts of power, 1.74 meters per second squared gravity dose. That's more than enough to hold a human on the floor and grow plants. Half of that is what's recommended to grow plants in space. So at 10 watts of power, which would be benign to humans, and 20 watts benign to humans and plants, we could hold and create the artificial gravity environment into a spacecraft. So you wouldn't have to rotate these things around if you didn't want to, or you could fly into deep space where, if the sun isn't effective for you anymore, then, high level, you don't have to rotate the craft around. A lot of reasons to do it, a lot of reasons to utilize that ability, like less exercising in space. Some of the future things, and to show this one, and we'll wrap this up. Flying craft, I don't know, I've always been fascinated by individual one-man system. I actually have that up at the farm. The basis or all of the structure has already been made, waiting for the motors to be perfected. And so where there's a will, there is definitely a way. This is the, our solar system. It's way out there. You don't have something to get from point A to B real quick. Then the logistics to support, which I don't have to tell you guys, understand that. But I mean, carrying all the food, all of the other stuff that you got to have, it's mind-boggling. You got to be able to consume 5,000 calories a day in space. That's what it takes. That's what they've said. You got to carry a lot of stuff with you. So if it's more than one person, I mean, you're talking hundreds of feet worth of spacecraft just to manage the stuff. Plus growing, I mean, the amount of space it requires to grow stuff. You need to be able to get from point A to B quickly. So you carry minimal amount of food, resources, And if you're operating on battery power, you don't need to lug a bunch of fuel with you. You don't need to land on, particularly like, for example, Mars, melt water, create your own fuels, because if you can't do it, you can't come back. I mean, to think about it, I guess, as early pioneers is exciting in one respect, but it's dangerous as hell. Now, if you can do this and do it in an appropriate way where you don't have to risk the crew's life to produce fuel, then I'm all for using the electric propulsion in this particular environment. Anyway, so this is the what we envision. We're building the full-scale Bluebird would be 30 feet by 30 feet, can hold up to 7 people. I'm still holding out for that. The prototype I have in the garage is 7 by 7. So it's a quarter scale of it. And then here's our last shot of going to Mars. And if I could get them to get me the money to go to the space to demonstrate the motor, I'd definitely take it out of orbit after a year of testing. I'd definitely show them that you can go someplace. With a 10-pound variant, we'll get there. Anyway, that's about it. That's the latest updates of what we're trying to do and accomplish. And I'll leave you with this picture. We're 26 million light years out from the core of our Milky Way galaxy. We'll only be able to explore potentially within the local star group, which is less than 1,000 light years. That's nothing. The Milky Way is 200,000 light years across. So that's my story, and I'm sticking to it. Questions?
Well, David, thank you, sir. So let me do this. I want to, let me see, I'm going to remove the spotlight and okay, I'm going to stop sharing on you there for a moment. Let me put this thing on gallery view. Everyone, please give David Perez a giant applause. Sir, thank you so much for presenting today. That was a wonderful and incredibly in-depth presentation. So thank you very much. I can't thank you enough for coming and presenting that. That's, you guys have done a lot of work since the last time you presented also.
Well, there's still a lot more to discover and to research. It's never ending, really. Like at our proposal has put in for over 10 people. I don't want to have a group. I need a small group of people. Right now, it's just the 3 of us. We have other ancillary people on the outside, but they don't do the technology that we do.
Yeah, no, that makes sense. Well,